Tonight, when you glance at your phone to check the time, you are doing something that took humanity thousands of years to figure out. Not checking the time, trusting that light arrives the moment you need it. You assume light is just there, instant, immediate. You have never once wondered how long it took to reach your eyes. But someone did wonder, and the answer they found changed everything. His name was Ole Rømer. He was a Danish astronomer working in Paris in the 1670s, and he was not looking for the speed of light. Nobody was. The idea that light even had a speed was considered almost absurd. Light was just light. It arrived. It did not travel. Rømer was doing something far more boring, or so he thought. He was trying to fix the world's clocks. This sounds strange, but in the 1670s, keeping accurate time was one of the most important unsolved problems on Earth. Ships crossing oceans had no reliable way to determine their longitude, their east-west position, without knowing the exact time. And without knowing their position, they ran aground. They got lost. They died. Thousands of sailors every year. The problem of longitude was the moon landing problem of its era. Governments offered enormous prizes to anyone who could solve it. One proposed solution was to use the moons of Jupiter as a clock in the sky. Jupiter has 4 large moons, discovered by Galileo in 1610. They orbit Jupiter in precise, regular intervals. One of them, Io, completes a full orbit in roughly 42 hours. The idea was that astronomers on ships could observe when Io disappeared behind Jupiter and use published tables of those disappearances to calculate the exact time, and therefore their longitude. A celestial clock, universal, available to anyone with a telescope. But the tables kept being wrong. Rømer was tasked with building better tables of Io's orbit while working at the Paris Observatory under the astronomer Giovanni Cassini, the man who had first noticed the problem. Cassini had spotted something odd. The timing of Io's eclipses seemed to drift. Sometimes Io disappeared behind Jupiter a few minutes early, sometimes a few minutes late. Cassini noted it, shrugged, assumed it was some irregularity in the moon's orbit. He moved on. Rømer did not move on. He stared at the data. He mapped out every observation of Io's eclipses that the Paris Observatory had logged. And he noticed something that stopped him cold. The timing errors were not random. They were not caused by the moon behaving strangely. The errors followed a pattern. When Earth in its orbit was moving toward Jupiter, Io's eclipses arrived early. When Earth was moving away from Jupiter, the eclipses arrived late. The discrepancy built slowly across months, and then reversed itself across the next 6 months. This was not a moon problem. This was a geometry problem. Rømer made the leap. The only explanation for this pattern was that light itself was taking time to cross the distance between Jupiter and Earth. When Earth was closer, the light from Io's eclipses arrived sooner. When Earth was farther away, on the opposite side of its orbit, the light had to cross an additional distance, a distance roughly equal to the width of Earth's orbit around the Sun. That extra distance was taking extra time. About 22 minutes, Rømer calculated, though the true value, as later measurements would show, is closer to 16 minutes. Light was not instant. Light had a speed. In 1676, Rømer published his finding. He made a bold prediction. The next eclipse of Io, scheduled for November 9th of that year, would arrive exactly 10 minutes later than the existing tables predicted, because Earth was currently moving away from Jupiter. He named the date. He named the delay. He staked everything on the outcome. The eclipse arrived late, exactly as he predicted. But science did not applaud. Cassini, his own supervisor, rejected the interpretation. The most prominent astronomers of the era, men who spent their careers measuring the heavens, looked at Rømer's data and dismissed the idea that the results proved what he claimed. Some thought the timing errors came from imperfect observations. Some thought it was atmospheric refraction, a bending of light by the air that made things appear where they were not. They had a dozen other explanations. The simplest one, that light had a finite speed, was not one they were willing to accept. Part of the resistance was philosophical. For centuries, the dominant view held that light was either instantaneous or so fast as to make the difference meaningless. Galileo himself had tried to measure the speed of light in the 1630s, placing two men with lanterns on hilltops and having them signal each other. The delay he measured was just his own reaction time. He concluded that light might be infinitely fast, or at least too fast to measure with the tools he had. The idea that Rømer had detected a speed, sitting at a desk in Paris, staring at Jupiter's moons, was not what most people expected a breakthrough to look like. Rømer died in 1710. He never saw his discovery fully accepted in his lifetime. The vindication came from England, 16 years after he died. James Bradley was an English astronomer who discovered something called stellar aberration in 1728, a slight apparent shift in the positions of stars caused by Earth's motion through space and the finite travel time of light. Bradley was not trying to confirm Rømer. He was trying to measure stellar parallax, a completely different thing. But what he found was the same truth. Light had a speed. It was finite. And from his data, he calculated that speed, roughly 301,000 kilometers per second. That is within 1% of the value we use today. Every subsequent measurement confirmed Rømer. By 1849, the French physicist Hippolyte Fizeau had measured the speed of light on Earth itself, using a rotating toothed wheel and a beam of light bounced off a mirror 8 kilometers away, one of the most elegant experiments in the history of science. By the time Albert Einstein built his entire theory of special relativity around the constant speed of light in 1905, the number was known with extraordinary precision. The speed of light, 299,792,458 meters per second, exactly, is now one of the most precisely defined constants in all of physics. So precise that in 1983, scientists used it to redefine the meter itself. A meter is now officially defined as the distance light travels in a vacuum in 1,299,792,458th of a second. The speed of light does not depend on what we measure it with. We now measure everything else in terms of it. Consider what that means. Every GPS satellite in orbit above you right now is sending signals to the device in your pocket. Those signals travel at the speed of light. The GPS system accounts for the time it takes those signals to arrive, nanoseconds, billionths of a second, to calculate your position to within a few meters. If the software did not account for the speed of light, your GPS would be wrong by kilometers. The Maps app you opened this morning, the one that told you to turn left in 200 meters, only works because a Danish astronomer in Paris looked at a moon of Jupiter and refused to accept that the numbers made no sense. Every fiber optic cable under the ocean carries data at close to the speed of light. Every camera you have ever looked into fires a shutter at a speed measured against it. Every radio telescope that has ever listened to a distant galaxy is accounting for how long it took the signal to arrive, sometimes billions of years. The speed of light is not just a number, it is the fundamental limit of the universe. Nothing with mass can reach it. Nothing we have discovered travels faster. Rømer found it by staring at a clock that was running slow. He was not looking for the speed of light. He was trying to help sailors not drown. He sat in a cold observatory in Paris, squinting at moons nobody else found interesting, and he noticed a pattern where everyone else had seen noise. He made a prediction. The universe delivered the answer, and then the world looked away. Tonight, when you glance at your phone to check the time, light from the screen crosses the distance to your eyes in less than a nanosecond. You do not think about it. You do not have to. But someone, 3.5 centuries ago, stared at Jupiter long enough to prove that the journey even happens at all.